everyone. So let's get started. Welcome back to the afternoon session of the AAL, day 2. And we are going to open up with the second keynote of the day by Professor Claudia Nolan from the University of Brasilia. And Claudia is going to be talking to us about efficient theorem proving for modal logics. So please, Claudia, take it away.
Thank you. First of all, I would like to thank the organizers of this conference for inviting me. All right, I'm sorry, is this working?
Yeah.
Yeah? It's not. Then we didn't switch on.
It's switch on. It should be working. Yeah, it's really. Wait. On Zoom, can you guys hear Claudia? Oh no, there is no one on Zoom. Sorry, I'm just recording to myself. I think it. 1, 2. This one is working.
Okay. So I'll speak by the.
Oh, it doesn't have but. Ah no, now it's working. Sorry, yeah. Now it's on. Yeah, yeah, it's all.
All right. I usually speak very loud, but I think it's the jet lag. I flew from Brazil, arrived yesterday, and so my voice is a bit weak. So first of all, I would like to thank the organizers of this event for inviting me. I always find it very exciting to be in a kind of environment like this where we have people from very different backgrounds. There are people from philosophy here, mathematicians, computer science, everyone working with logic. And I think that's always exciting when we have people looking at the same problem with different eyes from different point of views. I am born and raised in computer science. And what I'm going to talk to you is about my experience on automating reasoning for modal logics. We suppose this should work. No, it doesn't. Oh, okay, so I need to. All right, thank you. So this is what I have learned so far from the implementing systems. I actually work on proof theory, but as I said, I come from computer science, which means that I actually always have implemented my systems. And I always see a good point on doing that, even if you are not looking for efficiency. You actually, by running systems, you actually can see things that you don't see on paper. And I think that maybe that also asked me to actually better tell you what I mean by efficiency. We had some talks about modal logics already, and if you are not aware exactly of all applications, it's all fine, but this has been used to represent and reason about very complex problems in computer science, in philosophy, mathematics, and so on. We can talk about temporal reasoning, epistemic reasoning, deontic obligations, choice, actions, and so on. So I think Dirk's talk in the morning was very good because he was showing different modal ways, modal systems with different meanings and intended applications. And that's very good. The one good thing is about modal logics, and the ones that I'm going to talk about, they have all the same syntax, which actually make things look the same but very different when you're changing semantics. Once we have a representation of a problem, then we want to reason about the problem, the system that we are representing, what are their properties, and so on. And for doing that, you actually want some efficient calculus for doing the reason for you.
Obviously. So it's not working again. So there are some different morphism of proof methods for doing this. We have seen sequent calculi today. There are resolution calculi. That was already talking about some of the resolution systems we worked together. We could also, the modal logic so I'm talking about, they could have been translated to first order logic, and we could then usually use some automated, then you don't see me anymore. And okay, I don't know if I talk on the microphone, if I speak to you. If I speak loud, it's fine. Yeah. Okay, so I better do like this. I am going to speak loud.
Yeah, I just pointed towards that because it's for the recording mostly.
Oh, all right. So we can actually translate things into first order logic and use theorem provers that are actually very efficient and so on. Obviously, those provers are not actually specialized to deal with the problems we are dealing with. Modal logics in general, they are decidable. The logics we are talking about, they are decidable. And first order theorem provers are not. Right? They are not complete. They are mostly refutational complete, but not complete in general. All we could do is provide a proof method within the language of a particular modal logic that we are using. I work in the second case. I am usually designing calculi for those logics. That means in our language, it's not exactly the language I'm going to talk about a bit more about this, but it's close enough to the language that we are actually representing our problem. And that's good for the user because he is going to see proofs in the language that's closer to the representation of their system. And obviously, again, even if you are using direct methods, meaning using the language of your choice of modal logic, then you can have different methods using direct methods or different proof methods using direct calculi. But I'm going to talk about resolution-based methods. So you have seen already what modal logics are. I am going to talk about monomodal logics, and I'm going to talk mostly about K, which are normal monotonic modal logics, but we have worked on logics that are similar that don't have those properties. So we have a set of unary operators. They are indexed by natural numbers. I don't know, a finite set of index firm representing by A. And they are unary operators. They have box and diamonds. And when we are evaluating formally, we are evaluating them with respect to a structure that we call a crypt structure. This is basically a set of words, and these words are related to each other. It's a binary relation for each of the indexes we have. And when we are talking about the box modality, what we have is, if I have box A, I need to find a structure, which is a relational structure as this graph that's over there. And I'm going to find, I'm going to look at all words that are related to this one and see if phi is true over there. And if it is, this formula is satisfied. And if I want to talk about the dual, which is the possibility operator or the diamond, then I need to find one word, at least one word that's satisfying, that's related to the word from where I am reasoning, and that satisfies the formula. For instance, this one. As you can see, I'm always looking for what when I'm trying to evaluate a formula, so we can actually restrict the structures we are dealing with. It doesn't need to be any kind of relational structure, but we can actually just consider some root for our structure, which is in blue here, only the words that are accessible from that. And more than this, we can actually work with what we call the unraveling of this word, this structure, meaning that I am just copying the relation over and over and over, as I'm doing here on the right-hand side. And I am copying the relations I have and so on. Obviously, this might lead to infinite structure. But a few pages of proof later, you can show that you can actually link this structure to a finite tree. And this finite tree has the depth or the height of the degree of the formula we are considering, which is exactly the nesting of a modal operators, the maximum nesting of modal operators of your formula, right? So we can work always with finite structure. The problem is decidable, and that makes things somehow easier. I'm going to tell you why I'm showing you the trees. We don't need to work with trees, but that is going to help to talk about what I mean by efficient. That tasks when you are considering modal logics, we talk about local reasoning, which was mostly what Dirk was talking in the morning. And that means that I need to find a structure, I need to find a word or a point in this structure that satisfies my formula. And we can talk about global satisfiability. Dirk also mentioned that, something that I need to find a structure where my formula is true in all the points of that structure. And we can talk about satisfiability, local satisfiability under global constraints. If you are thinking of a computing system, you have some properties that are general of the system, but you want to see local properties hold, and this is how we do that. And those reasoning tasks, they are very different. Well, they are different from each other in the sense that they have even different complexity. So it's space for local reasoning. Is that time complete for global reasoning? And satisfiability on the global constraints is also X time complete, although you can read from that. So it's a difficult problem. It's not an easy problem, right? And you want to solve this in the best way you can so that your user is not waiting for an answer from your theorem prover for some generations. Is that okay? Now, as I said, I'm using resolution, and Dirk has presented this and better than I could, which is this beautiful rule here. We have something clause of for, which is a function of literals, and a literal in L is resolved in the first clause is resolved with the complement of that literal, not L in the second clause, and we obtain resolvent that is the remaining of the clause. So resolution is just this rule. It's a very simple rule. It sounds complete and terminating from propositional logic, and it is kind of easy to implement. So when resolution came about in the 60s, it actually changed what automated reasoning was about. Oh no, it was the very beginning of automated reasoning, but changed what automated reasoning was about, because for the propositional case, it might not look that much, but for the first order case, we had unification on demand and things like that that actually made it very interesting way of implementing calculus. And most of the reasoners, even to this day, are based on resolution. So it is a rule that actually asks for combining all the clauses that you have in some kind of normal form, and that may be very expensive. So you need to be careful in the way that you are implementing so that it's not a naive way. This is the algorithm. And most of the provers nowadays is to implement exactly this algorithm. You start with a set of clauses and you repeat. You choose two clauses with complementary literals, you resolve them together. If the resolvent is not redundant, then you add to your set. We are adding constraints to our set of clauses until you generate the empty clause, which I'm calling false here, or you have no other possible new conclusion. You cannot generate anything here. And if you look at this algorithm, this is how we implement this. It is this simple. It's not very different. Obviously, you need to be careful in the way that you're implementing. The first thing that you need to be careful is that we need to do pre-processing of our input. We need to generate clauses, and we need to generate clauses in an efficient way. The second thing is that this algorithm is actually non-deterministic. And it's telling us that we should choose the literals, and we should choose literals in clause in such a way that leads to completeness, right? And non-deterministic algorithms are magical, but computers are not. So we actually need to do this thing in a way that is actually reasonable. And the third thing that is in this algorithm that's actually very important is the notion of redundancy. And there are several different notions of redundancy that we need to use. And for termination, we really need at least two things. We cannot admit tautologies in our clause set, and we need to check for repetition, right? And if that's true, we can actually ensure termination. So this is important. I'm going to talk a bit two things. One is but the most important really here is the clausal form. For propositional logic, everyone has seen already logic 111, that we can put everything in conjunctive normal form, and that is the way of doing it, and there is just one normal form. But there are different ways of doing that, right? And that's important. For modal logic, that's different. There are different modal normal forms, and the normal form you choose has impact in the way that you are actually producing your the shape of your calculus and actually how efficient that can be. So this is what we had seen when we did logic first time. Your lecturer told you that you would eliminate implications, you use the model put negations in words, use elimination of double negations and so on. And then you would use distribution to put things as a conjunction of disjunctions using that rule over there, which is the distribution rule, right? And we don't need to look at this for very long to see that 5 on the left-hand side is repeated twice on the right-hand side, and that actually leads to a combinatorial exclusion of your clause set. Now, but we have actually ways of dealing with this. This is exactly the way that is done in Cook's proof for NP completeness, the NP completeness of satisfiability of theorem proving for propositional logic. He uses creating renaming, which means that we are actually adding new symbols to our formula together with definitions in such a way that we can actually keep things, we can keep satisfiability, and moreover, we can actually keep a reasonable size of the formula. The idea is very simple. If you have never seen renaming before, don't talk about the introduction of literals and definitions today, but the idea here is very simple. If you have a disjunction of conjunctions and you try to use distribution, then you are multiplying it grows, right? So what we are actually doing is introducing these new symbols, and these new symbols are going to have the meaning that we want. We, for instance, can add T1 as a new symbol and T2 as a new symbol that is defining the first and the second conjunction. And instead of writing the formula this way, we write this. You cannot read the second line, but I think the first line you can read. Instead of having, I say now that my disjunction is T1 or T2, and I say what T1 and T2 are. I mean, I just introduced the definitions of those new systems. And as you can see, I am putting names in this syntactical structure of the formula, so there cannot be more symbols than the size of the formula, and therefore I am keeping complexity low. Now, for propositional logic or first order logic means that we are keeping a good size. We are taking input, we are producing a causal form, and we are keeping this with a very reasonable size, which is actually linear on the size of the original formula. But renaming is also important for modal logic in another way, which is by separating different contexts for reasoning. If we are talking about multimodal logics, you actually want to separate the reasoning of what we call agents. We want to have in time for reasoning about knowledge of agent 1, the one for agent 2, and so on. And we can actually use renaming for doing that. And Please don't take note of the second line that I'm showing here now. The idea is something like this. I am introducing a new symbol T1, and now T1 is the name of the formula diamond 2P, right? But if T is like this, it's not right, because we need to be very careful that T1, or the meaning of T1, because this is a modal formula, needs to be known in the whole of the structure that we are thinking, right? So in the way this is written, it's not actually giving meaning to the formula diamond 2P exactly where I need it. For that, what we do actually is using what we call a universal operator. The universal operator is the box star over there. This is an operator that's telling, it's a syntactical way of saying that the meaning of the new symbols are going to be true in every point of my structure, right? So the second form here now is saying that T implies diamond 1 to 1, and everywhere it's true that T1 implies diamond 2. So the meaning of T1 is now available wherever I'm doing my reasoning, and not at the only point that I was starting reasoning from. And the use of the universal operator actually mimics the renaming procedure for first-order logic, where when you are introducing new symbols, those symbols are universally first-order. So they are true everywhere in your structure, right? So this is good. So now we have a way of also separating, not only getting a normal form that is of reasonable size, but also separating the parts of the formula that are related to different parts of the logic. I'm presenting here two different normal forms. I'm talking about the first one now, and then I'm going to tell you why I am actually going to the second normal form, and I think this is more efficient. Can you see this? All right. So here you see that I have a new constant, which is called start. This is just a place from where I intend to start reasoning, or a syntactical way of saying have a marker or a syntactical mark for the word from where I start reasoning. These are propositional clause, and here is where I have the renaming symbols being introduced, and that meaning, the meaning of everything that is renamed is true everywhere, is globally true. Okay? So keep in mind just the first part. I'm going back to the second in a bit. So when we have this normal form, then first of all, this is a normal form that's very simple. We have something that's representing the reasoning at the root of our world, which is represented by that start. Things that are true everywhere, which are the literal clause. And we have positive, what I call positive and negative modal clause, and they have a very simple form. On the left-hand side, I only have literal in both kind of clause, and in the scope of the modal operators, I also have only literals, and that makes the clause in a very simple format. And reasoning is completely separating the propositional and the modal forms, as I'm going to show you now. I know it looks like a lot of rules, but this is just resolution. And this is the solution taking in consideration different contexts. So you are going to see that the rules, they have mostly the same format, but what I'm doing here is resolution on the right-hand side of these implications here. And that's all. And here, I know it's an implication as well, but this is just a disguise for disjunction. And because box L has exactly the same diamond, not L has exactly the same meaning of not box L, those things are complementary, and I'm doing resolution. So all these three rules are doing resolution as exactly as in the classical case, but taking into consideration the different contexts I am. So if something is true everywhere and at the root, then it's true at the root. The resolvent is true at the root. If the both clauses are true at the root, then the resolvent is true at the root. And if something is true everywhere, then the resolvent is true everywhere. So that's it. And that's not very difficult to understand. Now, this one is a hyperresolvent, this is a hyperresolution rule. And hyperresolution rules, they actually don't generate all the consequences of resolution. They actually eliminate some steps. And the idea of this rule, which is kind of big, it's actually very similar to what Dirk presented today in the morning, where you had your sequence being iterated over by the curve rules until you get a very big rule with different modal operators. And the idea here is simple. The idea is that the boxes are saying that something needs to be true in all the words that are accessible. The diamond saying that something needs to be true in at least one word that's accessible. And we have this clause here in the premises that's saying that those constraints are, or this clause is giving constraints that are true everywhere. Now, if you look at the left-hand side of those rules here, and you actually have them to be all true at some word in your structure, what happens is because of this diamond here, we need to have a successor, and this successor is going to have not L. Now, everything that's inside the boxes need to be true because now I have an accessible word, and then I'll have not L1 to not LM in there. But this clause here, the first clause here, is also true everywhere, and then I can resolve not L with L, L1 with not L1, and so on, meaning that this word is contradictory. And because this is contradictory, I don't want the left-hand sides all those implications to be true, right? And this is exactly what the resolvent is saying. I don't want all those things to be together true. Right, so I'm adding the constraint to my clause set. One thing that's actually important, there are two more rules, but before I'm going to the rule, how I'm going back now. How do I go back? Yes, I tried. Oh,
Again?
okay, I did. Okay. So one thing that's actually important is that if you look at those rules, there are more rules that I'm showing to you. But if you look at those rules, they are actually separating things in a very nice way. I'm always having all my resolvents are propositional, which means that I don't have modal reasoning besides the reasoning that I need to create new propositional constraints within my rules. So here, everything's propositional, 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 propositional. And I'm going here, my resolvent is propositional, although I'm applying modal reasoning. And we have two more rules that have more or less the same spirit of the one I present in detail, but again, everything is propositional here. So reasoning is completely separate. We are doing propositional reasoning and we're using everything that we know how to make the calculus for the propositional part a good one, efficient, and everything. And modal reasoning is not generating new modal constraints. We don't need those new modal constraints. And this is a good thing, because every time you generate new modal constraints, your problem or the way you need to deal with things makes it more difficult. Now, as I said, I implemented this. I implemented everything that I do, but I have implemented this. And I was having trouble trying to get to solve very small problems. And if you work on automated reasoning before, the first thing that you blame is I didn't do the pre-processing right. And then you go back and you do the pre-processing right. You do simply simplification, you improve your transformation to the normal form, you eliminate redundance, you use pure literal elimination, you actually remove everything that you want, and it's true, I wouldn't get good results. And then I implemented what we call refinements for resolution. I implemented negative resolution, I implemented positive resolution, I implemented subassumption, forward and backward subassumption, I implemented ordered resolution, and I wasn't getting good results. And I was looking at, and if you actually work with resolution, something that's very interesting is that we actually generate a lot of information that we do not use in our proofs. And I was looking at that, and I was looking more what kind of information. I mean, I can't do much about the propositional part, but I can do something about the modal part. And when I'm looking at this, I'm looking at clauses there. Obviously, I was looking at big clauses, not something as simple as this, but this gives you an idea of the problem. If you look at this formula here, diamond, diamond P, and box not P, this is not contradictory. It says like I'm walking 1, walking 2, and not P's, and P is true. And the box is just walking 1. So the P's and not P's, they are not contradictory, right? Not in a relational structure. The translation would give something like this. I'm not showing the transformation, but as I told you, I am introducing a new symbol. This is the name of box T1. T1 is the name of box P, so this first part here. And also T0 is denoted the name of box not P because this is a conjunction, right? And now I'm looking, resolution is not going to look at things, it's looking at the clause now, and it's looking at box P, diamond P is box not P, diamond P is not box not P, so they look contradictory to the computer, and it's going to generate a resultant, not T0 or not T1, which is useless because it's not actually talking about any modal constraint of my problem, right? And if you take a small problem like that, I'm generating just one useless resultant, it's okay. But if I have a big problem and I'm generating hundreds and hundreds and hundreds of useless resultants, then that's going to affect everything. However, as I told you, it's actually simple to see from the syntactical structure of our problem that this is under 2 diamonds or 2 modal operators. This is under 1 modal operator. And things that are under 1 modal operator and 2 modal operators, they don't conflict, right? So what should we do? Well, we should look at the syntactical structure of our formula. And from the syntactical structure of our formula, we are actually taking the measures that we need to avoid resultants that are useless. For instance, the syntactical tree of this formula here is showing us that the formula itself is propositional. When I am looking at the depth of the operators, this is at depth 0, this is at depth 1, this is at depth 2 of modal operators, this is at depth 0, this is at depth 1 of the modal operators. This is showing me the measure that I need for the scope of how many operators my symbols are. And I told you that, well, we can actually think of the models of, for this kind of logic, they are trees, or they are tree-like in this case, okay? And what I have here, I mean, this tree is very simple, but at the whole root of my model, I have the formula. The whole formula needs to be satisfied. But as I'm walking down the tree, the second level or the first level, this is level 0. And the first level, I have satisfied diamond P and not P. And from the structure of my formula, I only need to satisfy this P at the second level, right? The syntactical measure, which is called A level corresponds to what we call a layer in the structure of the model tree. And the layer is just the distance from the root to where I am actually evaluating my formula. From this, we actually got the second normal form that I showed you before. And this normal form now has labels. And those labels, ML, it's model level where the clauses actually occur in my original formula. And what this is saying is that I am now evaluating things exactly at the level they occur in this spatial structure, which corresponds somehow to where they occur in the semantical structure. How this helps? Because now I can only do resolution when my labels unify, right? So I cannot generate the resolvent that I told you before. This is the same problem I had, and with the new translation, this is a clause at level 1, this is a clause at level 2. The labels do not unify, and because they do not unify, I'm now resolving them together. No step taken. This set is saturated, and because it's saturated, and I haven't found damped clause, this is satisfied. However, I can still, in this way, again, I cannot do any step here. P and I will not P are not contradictory. They are different levels, and I'm fine. And I can actually have problems that are global. These are marked with star here. And now I can actually solve global problems by saying, well, if this is true everywhere, then this not P and this P actually are contradictory, and I can solve them together, right? I can resolve them together. And by doing that, I have a calculus that can do local reasoning, can do global reasoning, and can do the combination of global and modal reasoning just with one set of rules. Now, the calculus is very similar to what you have seen before. It's not very different. Again, I only have positional resolvents, but they are now only generated the labels for the premises of what we call parents are unifiable, right? And that actually generates much better, actually gives a much better implementation of the calculus. And this was again implemented. So I had implemented what we called GMR before, with the calculus with the box star, and I implemented this one. This is in the KSP prover. This is already almost 10 years old prover that's being maintained. It has both the global and the modal layered resolution calculus. As I said, I mean, it doesn't say, but I'm saying now, both calculi are sound and complete for multimodal logic K. They are actually decision procedures for both global, they actually have very good performance with respect to state-of-the-art provers. And for local problems, layered is way better than global. So we actually have a lot of results with benchmark a lot to get things to see if that was actually really promising as it looked like. I'm just showing samples of things. I mean, I have more data than this, but it's just to show that on the left-hand side, I have a particular benchmark where we are actually looking at the results of doing the this is other resolution, but you don't need to bother. It's not about other resolution. What it's saying is that if I am use the first calculus I showed you, then as far as the formula grows, I'm taking more time, and for layered resolution, it's flat. And same goes for satisfiable formula. So actually, is a good the separation that you get from using the labels and the syntactic structure of the formula actually leads to both good performance, not only for unsatisfiable formulae, but for satisfiable formulae as well. Okay. So I can't tell you about benchmarks and things like that, but again, I'm just going to see the picture of things. And this is different implementations of refinements we had. I told you, I actually had implemented already other resolution, negative resolution, and everything. So we really wanted to see what the effect of this was. And we can see this is, if I could actually, okay, better. All right, so plain resolution, can you please stop? No. I'm sorry. I just want to get rid of that thing from mine.
Yeah, it has to,
Okay.
1 second. It has to go on its own. It's not so you just have to let it here. So let's put it full screen again. 1 second. Okay. And now we just move let's move it over here, and then it will eventually go away.
Okay, that's fine. Thank you. So we have actually implemented different kinds of resolution, and you can actually see that, positive resolution wasn't very good. I don't know exactly why to this day, because positive and negative resolution perform mostly the same. Plain resolution is just binary resolution with no strategy. We have implemented negative resolution, ordered resolution, which is the red one, and a combination of negative and ordered resolution. It's not negative or ordered resolution, but a combination of them both. And you can see that the refinements of ordered resolution and negative resolution actually perform much better than just plain resolution, which is also showed that you can actually use strategies and things like that. Our refinement for the resolution, ordered resolution is not consequence complete. Negative resolution is somehow consequence complete. It generates all the positive calls that you need for finding and proof. But ordered resolution is not. So we need to actually adapt the normal form to implement those things. It's not a pure adaptation. I mean, it's not just using ordered resolution as it's given. We need to do some work to actually adapt methods for first order logic or propositional classical logic to modal logic, because it doesn't work from the shelf. But even if you actually introduce new symbols that we need to do when we are doing ordered resolution and negative resolution, they perform much better. And now this is again a bit old, but we tried all the proofs that were available, including transformation of the problems into further logic using vampire and a functional translation that's optimized. Our proof using ordered resolution was much better than for this particular benchmark was much better than the others. For the benchmark that's actually used has different families of problems with different structures, which is the LWB, and we perform as good as the others. I mean, we are in the middle. Spartacus, which is a tableau system, is actually better. I don't want you to read that much. I mean, don't worry about reading. I'm telling you what's important about stable. And what's important about the stable is that we can actually get a lot of, we are doing very well in many problems. And there are problems that are very difficult for all provers. For instance, there are pigeonhole problems and stuff like, and pigeonhole problems. And pigeonhole problems are just pigeonhole propositional problems that, and the tree is only height tree and big propositional difficult problem at the end. And branch is that you actually need to do a lot of, for tableaus would be means that you would have actually several modal branches to deal with. And this is where we don't go well, because I mean, when you are actually implementing things, you need to be sure about what you can do with the techniques that you are implementing, where they are good and where they are not. If I am actually trying to separate my problem in layers, as I did, I'm actually separating different model problems to be solved. And if I don't have enough layers, then it's not going to be good, right? So the problems of this particular benchmark, they have very small depth. The depth is going to 3 with big propositional problems, and then the prover goes much worse than the others, like it's here. And this is an incremental SAT prover with Tableau and SAT mixed, which could do much better. Now, the prover also implements the calculate for all the things that are in the model queue. I'm not talking much about this, but they are, if you look at the left-hand side here, we have K, which is the logic that I have just told you about, the calculate, and this is inclusion. It's a Hess diagram that you should read like this. So this is the weakest logic, and this S5 is the the strongest logic, meaning we prove a little here and we prove a lot over there. For multimodal logics, they are all in P-space, which means that all those logics, they can actually be and K is P-space complete, which means that it can always transform problems into a problem for K, and actually use the prover for K for solving those problems. So we actually had already some, we actually had full automation for all the logics using the global calculus, because it was something that a calculus that I actually produced Claudia Jackson, and then an extension with Jean-Marc and Claudia Jackson in 2014. However, the prover, its strength is exactly how, as I told you, when we can actually separate things and actually deal with global or local problems. So this actually led us to develop special techniques for transforming local problems using what Kat would call global to local reductions. It was inspired by him. We actually improved on his result by doing that, which is a good thing. So we have now local reductions for all 15. Oh, we had local reductions for all 15 monomodal logics using a specific normal form based on sets as labels, which is not implemented, but we translate into the language of the prover. We actually improved on Kraft's result by giving better upper limits for the transformation based on single levels as it is implemented in prover. This leads not only to the implementation and therefore full viability of a tool with 2 different approaches for all 15 logics, but we also have an axiomatic translation that can be used by any other prover in such a way that they can actually transform problems in any of those logics into problems of K and use that for solving reasoning problems then. And because I think you mentioned the difficulties of finding benchmarks, even the benchmarks for modal logics, they are not actually, we have some, but they are not actually many, and they are not challenging anymore. And for the logics that we are considering in the model cube, then they are not challenging at all. I mean, they are mostly toy benchmarks for people testing particular capabilities of their own provers than actually talking about the specifics of the problem. So we actually generate new benchmarks for all those logics that are more challenging than the existing ones. Now, to sum up, and then we actually implement those things again, don't try to bridge. And the idea here is just to show that GMR is the one using the box star, and the MLR is the one using the model layer. And we can actually see that for some logics, for K, local is always best. But for some of those logics in the cube, where you actually have a lot of propagation, for instance, transitivity that's actually taking consequence beyond, S5, where reasoning is actually global, then the prover doesn't perform very well. And if you consider all the 15 logics, then you are going to see that the global calculus is actually better. Now, we have now 3 different normal forms, 3 different calculi, and 2 of which are fully implemented. The other one is is waiting until I have time. Another sabbatical retirement. No yet. So I asked, my question was if local is best, and local is best depending on the problems you are dealing with, right? So if the problem is actually has some kind of global nature, as in S4, S5, and those things, then it's not going to work. But it's going to work for model K and local K easily. We have also, because of all the things that we did in the past 10 years in the implementation, we actually improving on other results, and we have novel local reducers for all the systems in the model for KN, which is a good thing, and that is actually contributing to other people who are developing tools. We have new upper bound limitations for the transformations without sets. We have new benchmarks for all logics in the model cube and beyond. We have experimental evaluations showing the effectiveness and difference between the approaches, where one is better than the other. And it's very good to have different implementations, so tools are available for different needs of users. So what is need to do now? We are actually trying to, as I said, waiting for my retirement or another sabbatical, which I hope it's in a few years. Sabbatical is truly in a few years. My retirement, I don't know. So implementation are working, working directly with sets of labels. As you saw, we have single labels, but if we are working with sets of labels, then have an even more concise representation of clauses that occur in different levels, and then we can actually do less step of resolutions when we have clauses that are repeated, as in the case of S4 and S5, that you have them repeated over. And basically, that's it. Thank you very much for listening.